All right, good morning, everyone. So today we are going to discuss how to find approximate solutions to the differential equation of equilibrium. So in the previous lecture, we solved a few examples where we find closed form solutions. We found exact solutions to the differential equation of equilibrium. And these solutions that we found in the previous assumptions are termed strong form solution. In this lecture, we are going to show weak form solution. Now, I'm not going to discuss the reasons behind this terminology. It has to do with something called strong convergence and weak convergence in math. But to teach something like this, I'm going to have to teach you a few courses before going into explaining what these mean. In order to just show you an example of what weak form solutions are all about, imagine that you have an equation that says f of x is equal to 0. I would like to find what is x. For example, x minus 3 equals 0. And I would like to find x that satisfies this equation. Instead of working on this form and trying to find this, I'm going to call this g prime of x. And I'm going to integrate g prime of x dx to get g of x. And what do I know about g of x? What do I know about g? So g of x is a function of x. It can have any value. What do I know about g of x when x satisfies f of x equals 0? So, no, I know that g dash of x is equal to 0. So what does this mean? Slope is 0. That's correct, which means, therefore, f of x is minimum, sorry, g of x is minimum, maximum, or inflection point. Now, for the equations of equilibrium, g of x is minimum. And this is called the potential energy of the system. So instead, for me to find an approximate solution, instead of finding x that satisfies f of x is equal to 0, I'm going to find x that satisfies that this quantity that I created by integration is minimum at equilibrium. So I need to define this quantity first before I present those equations. So this quantity, which is called potential energy, is calculated as follows. The energy inside a continuum is equal to the sum of each stress component multiplied by the change in the corresponding strain component. So if this is sigma on 1, and this is epsilon on 1, and this is the relationship between the stress and the strain, as the stress increases from this point to this point, the strain increases from this point to this point, and this energy is equal to sigma on 1, the epsilon on 1. Now, the equations that we are going to cover in finite element analysis are the equations for linear elastic materials. So assuming that the material is linear elastic, I already know that sigma on 1 and epsilon on 1 will have a linear slope. And because they have a linear slope, the strain energy now from this point to this point, particular value of sigma on 1, this area is equal to sigma on 1 epsilon on 1 over 2. And so this integral from a 0 to a particular state of stress is equal to sigma ij d epsilon ij. This is per unit volume. Will be equal to the sum, let's not put the sum, is equal to sigma on 1, epsilon on 1 over 2, plus sigma to 2, epsilon to 2, over 2, plus and so on. 9 terms. Which is equal to the sum I j equal 1 to 3, sigma ij, epsilon ij over 2, or using the summation convention, sigma ij, epsilon ij over 2. So this linear, the elastic strain energy function inside a continuum for a general continuum, this is the equation: sigma j epsilon ij over 2. And if you replace, we know that the stress is equal to C multiplied by epsilon. The stress is equal to a linear function multiplied by C. For linear elastic isotropic materials, I can replace the stresses in terms of the strains and the strains in terms of the stresses using this one-to-one relationship where C is function of Young's modulus and Poisson's ratio. When you replace the stress with the strain or the strain with the stress, you end up with these two equivalent expressions. So whether you use this expression or whether you see this expression or this expression, they're the same, where mu and lambda are material constants. That can be used instead of Young's modulus and Poisson's ratio to simplify the expression. They were used by a person called why they're called Lami's constants. Now, the strain energy, if I'm solving beams, the total strain energy in a beam is equal to the integral of the strain energy with respect to the volume. This strain energy is the integral of sigma ij d epsilon ij. And in the beams, we said that the only non-zero components are sigma on 1. Non-zero stress components are sigma on 1 and sigma on 2. And the only non-zero strain component was epsilon on 1. And when we did the Euler-Bernoulli beam, we assumed that epsilon on 2 was equal to 0. And that's why you're only left with sigma on 1 and d epsilon on 1. The remaining terms are all cancelled. From here, I only get sigma on 1 d epsilon on 1 in a beam. Linear elastic, so I can replace it with sigma on 1 epsilon on 1 divided by 2. Integrating this over the volume, I'm trying to find the energy inside the whole beam. Integrating this over the volume, and remembering that we replace sigma on 1, or we can find a relationship between sigma on 1 and the moment, and we have a relationship between epsilon 1 and d2y by dx squared. I can find the total strain energy in terms of the moment and the second derivative of the unknown displacement, or the moment squared, because the moment is equal to ei d2y by dx squared. So whether you can use this form or this form or this form, they're all equivalent. Now we're going to use, at the end of the lecture, we're going to use this expression or this expression for the strain energy inside a continuum. We're going to use this expression and minimize this expression, because that is the function that I'd like to minimize. I'm just going to click here. This is the function g of x that I'd like to minimize so that I obtain the solution to my equilibrium equation. The finite element analysis, so just let me give you background first. There are two methods that we're going to introduce today. The Rayleigh-Ritz method, which depends on the potential energy of the system is minimum, and the second method is the virtual work method. The math behind both is equivalent for linear elastic materials. The equations might appear different, but at the end of the day, whether you use the Rayleigh-Ritz method or the virtual work method for linear elastic systems, it's the same. See? Even though equations might look different. And that's for linear elastic materials. Now the finite element analysis method is based on the virtual work method. If you understand today what I'm doing, then the rest of the course is just an example of this virtual work method. So let's look at the virtual work equations. So what is the principle of virtual work? The principle of virtual work is actually a mathematical concept, and we'd like to put some physics to it, or add some virtual work, which gives you some sort of a feeling that it's a physical quantity, although it's nothing but a mathematical concept. And the mathematical concept is the following. If I have this equation, the equilibrium equation, which says that F is equal to mg, or in other words, F minus mg equal to 0, I have a force in the spring, and this force is used to carry a weight mg, then mathematically, this equation, I can multiply anything by this equation. I can multiply this by x, or delta, or f, or g. I can multiply this equation by anything, I will still get 0, because f minus mg is 0. Now, if I choose this multiplier, and call it virtual displacement, and then imagine that I'm moving this object from equilibrium, a displacement delta star, then I get this equation that says F minus mg multiplied by delta star equal to 0. And since I'm starting from equilibrium, then I can say a virtual displacement from equilibrium will make F delta star equal to mg delta star. mg delta star, I'm going to call it the external virtual work. Why is it called the external virtual work? Because it's the work done by the external force acting on my system, which is mg. It's the external work acting on my system of spring and load, which is equal to the force multiplied by this displacement. This F delta star, I'm going to call the internal virtual work, which is equal to, if this is the spring force and this is the spring extension, it's equal to this work, or this integral of F multiplied by the displacement, which is internal because it's energy that's stored inside that spring. As I'm extending the spring with the displacement delta, there has to be some energy that is internal to that spring. There has some energy that goes into that spring, and that is called the internal virtual work. The internal, or the virtual work equation for a continuum, without having to go through the manipulations, you can look at how we arrived at those equations, look like this. And they, starting from the equilibrium equation, and the equilibrium equation was equal to partial sigma 1 by partial x1 plus partial sigma 2 1 partial x2 plus partial sigma 3 1 by partial x3 plus rho b1 equal to 0, and then repeat. This is equation 1, then equation 2, then equation 3. By doing the same thing as we did in the 1D example, where we take this equation and multiply it by something, and we take this equation and multiply it by something else, and we take this equation multiplied by something else, and I call this virtual displacement and do a lot of formula manipulation, I will get this equation that states the external virtual work is equal to the internal virtual work. Now let's look exactly at what these terms mean. The external virtual work is the work done by the external forces acting on my object when I move that object through a virtual displacement u star, where u star is any function u1 star, u2 star, u3 star defined on my whole domain. The forces acting on my continuum are two. I have the traction vectors acting on the boundary, and I have the body forces acting on the continuum per unit volume, which is basically similar to any gravity field that's pulling the continuum. So the external virtual work would be equal to the traction vector, this is Tn, multiplied by the corresponding virtual displacement on the boundary, because that force is on the boundary, plus the integral of that body force dot the displacement inside the object. So this is integrated over the volume, and this is integrated over the boundary. And when we start, maybe in 2 or 3 weeks, we are going to visit this equation again. So you have to know what each term means. So this is the external virtual work. The internal virtual work that happens when I move, or when I move the object by a virtual displacement u star, is equal to the stress multiplied by the increment in the strain, and the increment in the strain is equal to the strain that arises from this u star, and the strain that arises from the u star, I'm going to call it epsilon star. So let me write this down again. External virtual work is equal to the force vector on the boundary multiplied by the displacement on the boundary, this virtual displacement on the boundary, plus the body forces acting on the continuum multiplied by the displacement on the continuum integrated over the volume. And the internal virtual work will be equal to the stresses multiplied by the strains that arise from this virtual displacement. The strains that arise from virtual displacement, for example, epsilon 1 is equal to du1 star by dx1. So this is integrated over the volume. By equating these, and as you will see in the example in just a moment, by equating the external virtual work and the internal virtual work, I'm able to find approximate solutions. For beams, we replace the stresses with the moments on the, instead of the stresses inside a beam, we replace it by what we call the internal moment of the beam. And we also replaced the strains with, we made the unknown to be this y displacement. And so we are going to rewrite the virtual work equation for the Euler-Bernoulli beam, but it's equivalent to this equation, but after integration over the cross section. So the starting equilibrium equation, if you remember from the Euler-Bernoulli was E I d4y by dx bar 4 was equal to P. Again, this is just an equilibrium equation, and the virtual work principle states, well, I can say that this is equal to 0, and at equilibrium, because I'm looking for y that satisfies equilibrium, at equilibrium, I'm going to perturb or the structure by displacement that I'm going to call virtual y, the virtual y star, and this is a schematic. If this is the equilibrium equation, I'm going in the equilibrium shape of the beam. I'm going to assume that this equilibrium shape has moved by displacement y star, which could be anything. And after formula manipulation, you end up with this equation that states the following. The internal virtual work is equal to the external virtual work. What is the internal virtual work? It's a measure of stress multiplied by a measure of strain. The measure of stress is the moment, which is EI d2y by dx1 squared, multiplied by a measure of strain, which is T d2y, the virtual strain, that's the internal virtual work. The external virtual work is equal to, if I have a distributed load, it's equal to Q multiplied by the virtual displacement y star. And if I have a force here, V2, it's equal to minus V2 multiplied by y2 star, and so on. V1 multiplied by y1 star, m1 multiplied by negative theta 1 star, and m2 multiplied by positive theta 2 star. So this is the work, external virtual work done by the external forces acting on the structure. So let's now use this principle to find an approximate solution. And the first thing to find an approximate solution is that you have to assume something. If we remember, when we started, what is x squared minus 2? We started by saying assume x equal 1. And we also assume something else. We assume that x is rational. We're finding x, if you remember what we did in that solution, we're finding x that has the form m over n. We only looked for a solution in the space of rational numbers because we only looked for, if you remember, it was 1, 1.4, 1.412, 1.413. All these numbers are just rational numbers. The space or the possibilities of a solution only live within the space that I assumed x to live in. So I assumed x to be a rational number, and so all my solutions are the best approximation to root 2 within within the constriction that I put on x, which is I said x can only be a rational number because the computer that I'm using can only find rational numbers. Because it can only find rational numbers, I'm finding a better rational number that actually approximates my the exact solution of the problem. Now, if the exact solution happens to be a rational number, then my numerical method will give me the rational number that I'm looking for. For example, if I'm trying to find x minus 1.45 equals 0, and I use whatever method, assume x equal 1, and is a rational number, I'm going to maybe get 1, then the next iteration I'll get 1.4, then the next iteration 1.44, next iteration 1.45, and then whatever numerical solution method I'm trying, I will just get 1.45 and that's it. Any other iteration will get me 1.45, which tells me that I have achieved convergence and the solution is actually rational because any change of any iteration will just give me the exact solution again. However, I'm just repeating, if my solution is not in the space that I assumed x in, then I will never get that exact solution, but my solution will only be approaching the exact solution, which is root 2. And this is exactly what we do in the finite element analysis method, and we're going to start with an approximate solution. And that's the first thing is I'm going to live in a cubic polynomial approximation. The only possibility for the solution is I need a cubic polynomial approximation. I'm assuming that instead x is irrational, I'm saying x is a cubic polynomial function. And I'm going to use the virtual work method to find a displacement shape for the shown beam with these properties. Now, the exact solution looks like this. We've done this by hand in the previous assignment, so we know how to find this. Now, this is a continuous function, but it's not differentiable because right here, ei y power 3 on left is not equal to ei y power 3 on right. The shear looks like this. Now I'm going to, instead of using this approximation, this is the exact solution, I'm going to assume within this space of cubic functions, I would like to find a solution that best approximates this displacement. So what is the best cubic function that I can put here that would approximate my actual displacement? So this assumption restricts solution to the best possible cubic function to approximate the exact displacement. Now the exact displacement is squared, so it's a parabola on both sides. But because it's not really, it's not differentiable, and that's why I will never be able to actually obtain the exact solution. If this was continuous, if the shear was continuous, then the exact solution can be obtained using this approximation. Okay, so let's see how we can solve or how we can find the best possible approximation. So to find the best possible approximation, I need to satisfy certain criteria. And the first criteria, Y has to satisfy the stability of the structure. Which we call essential boundary conditions. I cannot choose Y that allows the structure to fly when I have already constrained the structure at 2 points, this point and this point. Because I have constrained the structure from moving, my approximate solution has to abide by this restriction, that the structure cannot move. These essential boundary conditions for an order Bernoulli B the essential boundary conditions are displacements and rotations. So when I look at my beam, I have constrained only the displacements. So I have made Y equals 0 at this point and Y equals 0 at this point. And so this function that I'm assuming for the displacement has to abide by this restriction. So at x1 equals 0, y is equal to 0, which leads to that first constant has to be 0. And at x1 equals L, y is equal to 0. So I'm going to put x1 equal to L in this equation. So I get 0. A0 is gone. And I will put A1 on one side. So this is A1, which means that Y is equal to A0 is gone, A1 is equal to this. When I replace A1 with this, I'm going to get the equation that says A2x1 x1 minus L plus A3x1 x1 squared minus L squared. So when you look at just the displacement, just to verify, put x is 0. This will give you 0, this will give you 0. The displacement here is 0. Put x is equal to L. This term will be 0, and this term will be 0. So this function really satisfies my essential boundary conditions of this, my essential boundary conditions of the structure being stable. So that reduces the number of unknowns to solve this problem to 2 unknowns. The 2 unknowns are A2 and A3. And the problem now is within this possibility that Y has this form, what is the A2 and A3 that best approximate my exact solution? you. So for this example, we're using the virtual work method. The virtual work method, I'm going to visit the virtual work equation. Where is the virtual work equation from order Bernoulli beam? Here is the virtual work equation, and then I see this y star. All I know is that I already found dy by dx1 squared. I have an equation for y, but I don't know what y star is. This is the virtual displacement. I can assume anything I want. But I have already restricted the space that I live in into that cubic polynomial equation. So the only thing I can assume for this y star is that cubic polynomial function. So I'm going to assume that y star, because I'm only living in that cubic, the space of cubic functions, I'm going to assume that y star is a cubic function. So for y star, I'm going to take the same form of y, but different constants. So I'm going to say y star. Well, it's not y, so I'm going to use a different constant. I'm going to call it a2 star. Multiplied by x1 minus L. Plus, instead of a3, I'm going to use a different constant, a3 star, x1 minus x1 squared minus L squared. I'm going to now write the internal virtual work and the external virtual work equations. The internal virtual work is equal to the integral of, this is the moment due to the stress inside the structure, and this is the virtual strain. Should have calculated then d2y by dx1 squared. dy by dx1 is equal to 2a2x1 minus a2l plus 3a3 x1 squared minus a3 L squared. Let me know if I'm doing anything wrong. d2y by dx1 squared is equal to 2a2 plus 6a3x1 and similarly d2y star by dx1 squared will be equal to this new constant, 6a3 x1. So this is equal to EI, the integral of 2a2 plus 6a3 x1 multiplied by 2a2 star 6a plus 6a3 star x1. Okay, just so that you're following. Which constants am I actually looking for? A2 or A2 star? No, not the star. The star is just the virtual displacement that I assume. I'm looking for these ones with the question marks, because this is the solution of my equation. Okay? So I'm going through this in details now. We're going to do this again for the finite element analysis. But at that time, we're not going to go that slow. So. And when you do this integral, when you perform this integral, you're going to get this. Now, for a reason that you will see in just 1 minute, I have written the equations as a multiplier by A2 star and multiplier by A3 star. You could have written in any form, but I've written the equation right now as a multiplier by A2 star and a multiplier by A3 star. Then I'm going to write the external virtual work. What external forces do I have on my structure? These, the reactions and the force are external forces. The displacement on the support is 0, so those are not doing any virtual work. I only have this P. It's acting downwards, everything I'm always assuming upwards. So for the displacement, so this is equal to P. External virtual work is equal to P, negative P, multiplied by the displacement star, the virtual displacement. And x1 is equal to L over 2. This is equal to negative P. This is displacement. And x1 is equal to L over 2. I will get L over 2, negative L over 2, multiplied by A2 star, plus L over 2, L over 2 squared, minus L squared, multiplied by A3 star. Now again, I've chosen to write this equation as a multiplier by A2 star and a multiplier by A3 star. Now why have I decided to write the equation in this form? Because I can control this y star. I can do anything to this y star. So I can assume that A3 star is 0 and A2 star is 1. If I assume that A3 star is 0 and A2 star is 1, what does this mean? If A3 star is 0, sorry, that's right. I can the equations of virtual work are true for any choice of y star. Because it's true for any choice of y star, I'm going to try a few things. What if a2 star equal 1 and a3 star is 0? What do you get? Internal virtual work is equal to external virtual work. A2 star cancels A2 star. This goes, this goes. You will get multiplier of A2 star in the internal virtual work expression is equal to multiplier of A2 star in external virtual work expression. And this is one equation. So I get that EI 4A2L plus 6A3L squared is equal to negative P negative L squared over 4. Now, the second equation, what if A2 star is 0 and A3 star is 1? This will go, this will go. A3 is 1, A3 is 1. I will get second, the multiplier of A3 star is equal to multiplier of A3 star. So you'll get EI 6A2L squared plus 12A3L cubed is equal to L over 2 squared minus L squared. This is equation 1. This is equation 2. Therefore, A2 will be equal to PL over 16 EI, and A3 will be equal to 0. When you solve these equations, you're going to get that A2 is equal to PL over 16 EI, and A3 equal to 0. Which means the best possible approximation under the restriction that y is a cubic function is y is equal to, we said A1 is 0. Let's look at the equation. This was my equation, A2 x1 squared minus x1L. A3 was 0, so A3 was 1. Which is equal to PL over 16 EI x1 minus. Now I have everything that I want. I have the displacement, I have the moment, shear. The shear is equal to the rotation is equal to the first derivative of y. The shear is equal, the moment is equal to the second derivative of the rotation, and the shear is equal to EI. So I have theta is equal to dy by dx. M is equal to EI d2y by dx1 squared, and the shear is equal to EI d3y by dx1 cubed. Now, how does this compare to the exact solution? Now, how does this compare to y exact? Now, let's look at y. y had this form, px1 over 48 ei. So it had this form. So clearly it's not the same, but how different is it? Now after assuming certain values for p and l, you can see that the approximate is always, in these particular problems, the approximate is always a little bit stiffer than the exact. So the approximate solution is stiffer than exact solution. Because I've constrained my structure, it can only deform within a certain allowable displacement. It usually is a little bit more, a little bit stiffer. And if you have some sort of a measure of the error, and your measure of the error is usually, okay, how far, what I'm trying to solve is this. How far is my solution from EIY power 4 equal Q? If I feel that this solution does not really satisfy the differential equation, then I can try a better approximation. And a better approximation would be, okay, well, instead of trying a cubic polynomial, I'm going to try a fourth order polynomial. And the virtual displacement in this case can only have this form. Now, why is this? How is this related to the finite element analysis? This is exactly what the finite element analysis does, but instead of assuming these equations or these approximations, we're going, as you will see in the next lecture, and I'm going to repeat myself, next lecture again, because this is the essence of the finite element analysis method, is that instead of assuming these humongous, or these polynomial equations for my displacement, I'm going to assume my displacement to have a very simple form. And the simple form is a collection of polynomial equations. Of linear equations. I'm going to assume that my displacement is just a collection of those linear functions, and just do exactly what I did here. Instead of assuming that y is equal to all these x1 cubed, x1 power 4, in the next lecture, I'm going to assume that y has this form. And then try to find these slopes, which will be the best to approximate my exact solution. Okay, 5 minutes. I'll give you 5 minutes. Yes, before. Yeah.
Actually, for this one, our basic assumption was the cubic function.
Yes.
Why do we finally found a parabolic function?
Oh, because A3 turns out to be 0. A3 turned out to be 0 from those two equations.
So, is it in parallel with, because it is not in parallel with our basic assumption, because our basic assumption is cubic.
No, our basic assumption, yes, but the parabola is a special cubic function. The parabola, let's look at the cubic function, sorry. The parabola is a cubic function with A3 equals 0. So the parabola lives in the space of my approximation. But the best approximation in that space is about.
This is the optimum.
Yes, this is the optimum, yes. Optimum within the possibilities that have this form. For this particular problem, I would expect if you move P maybe to the left or to the right, you might get the Q. I think the reason why this term is gone is because of the symmetry of the problem.